This video is a generic introduction to debugging. It corresponds roughly to section 13.1 of Applied Analog Electronics. Now, one of the reasons for teaching electronics to engineers who aren't electronics engineers is that it provides a good framework for doing debugging and for teaching debugging. The reason for that is that we have got things that can be changed quickly, and design can be modified and tested, doing iterative debugging. But at the same time, we've got real-world phenomena. It's not something where we're just doing simulations and the models are perfect. Whatever we think is going to happen is what's going to happen when we do the computations. With electronics, we often have design done with somewhat simplified models, and a lot of the debugging is checking that our models are adequate. So combination of real-world phenomena and rapid turnaround makes electronics a good medium in which to practice debugging. There are obviously very similar debugging things done in other media. Computer programming. Computer programming does a lot of iterative debugging. We don't have so much of the real-world phenomena going on there. The computers basically are almost perfect in that they do what they're told, and our debugging problems are just that we don't know exactly what to tell them. And sort of on the opposite side, we have bioengineering, or particularly biomolecular engineering, where we have very crude models often of what's supposed to be going on. We only have a vague idea how the real system's going to behave. And it takes a really long time to do an experiment, particularly if you're doing something like with stem cells, and it might take you months to grow them up and see if they differentiate the way you expect them to. So the electronics makes a nice balance between those. The debugging steps are about the same, though, in all forms of engineering, in the abstract. What they consist of is setting up an expectation of how the system or part of the system should behave under specific conditions. Then, observing the system under those conditions, comparing the observations with the expectations, finding any discrepancies between what you expect and what you observe, and then modifying the system based on the hypothesized causes for the discrepancies. You've got to if you get discrepancies, you have to go, well, why are they there? Maybe multiple possibilities for what caused that. Make some changes based on those hypotheses and test again. That's generic debugging in almost any medium. Where debugging is specific to different media is in how you set up those expectations, what your modeling techniques are, what observations you can make. Obviously, I can measure different things if I'm doing electronics than if I'm doing biomolecular engineering. They're just different observables. There's also, in the making up hypotheses about what the discrepancies are, a lot of that is domain-specific knowledge. You have to know, you have to understand your system well enough to be able to say, oh, this might be something that would cause that, this might be something that would cause that. And that's very domain-specific. I'm not going to be able to take an expert in electronic debugging to debug a molecular biology protocol, because the domain knowledge, what could go wrong, is different. But the basic steps of making expectations, making observations, comparing them, making hypotheses about the discrepancies, modifying something based on those hypotheses and testing again, that is universal, and it's a transferable skill from one field of engineering to another, one field of life to another. Okay, so the first thing is you need to have a model. You need to have something to base your expectations on. You can't just say, oh, well, I built this thing and it's supposed to do this. You have to have an understanding of how it does what it's supposed to do and exactly what it is that it's supposed to do. And those models are sometimes quite simple. Could be as simple as saying, oh, this is an amplifier, it's got a gain of 50. And all I need to know is that, if I put 2 millivolts in, I'll get 100 millivolts out. That's quite often an adequate model. Other times you'll have a much more complicated model, something that's got a page of equations for it. And that you're probably not going to be able to do in your head to figure out what it does. So something you nearly always need with electronics or even with biomolecular engineering, if you're doing synthetic biology or something, is you'll probably quite often have to do a simulation or a computation. Now for this class, we're generally going to have fairly simple algebraic models, and we can do our computations just with the plotting program like GNU-plot. Other courses, you will have to be solving differential equations or simulating differential equations. It's going to vary depending on what field you're in and how complicated a model you need. You're going to want to check the assumptions of your model. A lot of the stuff we do, for instance, involves voltage dividers. When you've got a voltage divider, it only works with that voltage divider equation if you're not taking any current out of the voltage divider. If you're taking current out, if you're violating the voltage divider criterion, then the simple model doesn't work and you have to switch to a more complicated model. So check that assumption. Saying, okay, I've got voltage divider here. I'm going to say the voltage out is going to be this much. Wait a minute, am I taking any current? No, great, I'm fine. Oh, I'm taking current. Is it significant compared to the size of the resistors and voltage divider? Is it close enough to zero that I can get away with the voltage divider assumption, or do I have to go to a different model and compute things differently? We often design as if our components were ideal components. We say, this is an op-amp. An op-amp has infinite gain, takes no current at the input, provides infinite current at the output. And of course, real-world components don't behave like that. And so you want to check some of the more obviously limiting properties of your components. For instance, on an op-amp, you might want to say, well, I know I can't get an infinite current. I can't get an infinite voltage. What I can get is it's got to be between the power rails. So is that going to be happening? It's got to be no more than, 30 milliamps. Is that going to happen? Checking those assumptions is a way to check to make sure that the model you're using for your design is a reasonable one. And if it's not, then either you need to change your model and use a more complicated calculation of what's going on, or change your design in such a way that the assumptions aren't violated. And which one you do often depends on other trade-offs. It's an engineering problem. Systems are complicated. It's what makes them systems, is that there are a lot of stuff in them. In order to debug a system, you can't handle the whole thing as just, oh, there's this huge thing and I've got to fix it, because it's just too much. What you need to do is to break your system down into smaller pieces, each of which you can understand, and hopefully each of which you can test independently. That's what your block diagram's for in electronics, and in many other forms of engineering also, is to take a large system and break it down into smaller systems and to try and make those systems nearly independent. There's some communication that they have with the rest of the system, and in this class I'm requiring you that on your block diagrams you be very explicit about what that communication is. Every one of your signals should have a clear label on it that says what it means, what its voltage range is, what its frequency range is. Anything that might be relevant for the blocks on either side of it is labeled on that signal, so that I can look at just the block and the signal on either side of it and see whether or not that's a consistent part of the design. And when I'm testing, I have labels on all the signals. I can go, okay, this thing's supposed to be 2 millivolts, check. This thing's supposed to be 100 millivolts, check. This thing's supposed to be 200 millivolts. Oop, it's not. Well, the 100 millivolts was okay and the 200 millivolts was wrong. So the block that's between those is probably where the problem is. Either a design problem, it wasn't supposed to be 200 there, I did a calculation wrong, or an implementation problem. I got the wrong resistor here, and so it's not putting out the voltage it's supposed to. So having the big system into little pieces is an essential part, not just of design, but of debugging. And so you need to have that block diagram done before you try and build, before you try and test. It's not, oh, this is a piece of documentation I do when I'm done with everything. It's an aid to doing the design and debugging. And your debugging will take a lot longer if you don't have that help. Along with the block diagram, breaking things into sub-circuits or sub-blocks, build your system a little bit at a time. Don't try and say, oh, I put the whole thing together and it didn't work. Well, of course not. It's way too complicated for you to have gotten it all right without making any mistakes. Build it a bit at a time. Test it as you build it. Oh, this part is supposed to do this. Yeah, it does that. Okay, put on the next part. That's supposed to do this. It doesn't. Oh, but here's a mistake. Fix that. Okay, now that's working. Build the next part. And by building it a small part at a time, you can debug a small thing at a time where your mental models are enough to understand what's going on. You don't have to have the whole thing in your head at once. So that requires a little bit of discipline. Testing as you build. And along with that, when you make your measurements, record the measurements. And don't just record, oh, it's 37. Put the metadata in. What were you measuring? What was the result of that measurement? What were you, possibly even what you were expecting to see there? If you're using something like the oscilloscope or pterodact, don't just sort of glance at the screen and say, oh, it must be good enough. Record information. Because later on, when something fails, it's, well, that part was working. Are you sure? Because quite often it was a misunderstanding at that point, and you don't have a record of, okay, it was supposed to be 100 millivolts. Oh no, it was supposed to be 200 millivolts. Screwed up there. If you don't have a record of what you measured, it's hard to go back and figure out, well, where was the mistake? Something's wrong here. The whole thing doesn't work. But, if I didn't keep track of what I did as I tested along the way, it's almost as if I didn't do the tests along the way. So keep records of what you do. I mean, in science labs, it's keeping a lab notebook. And it's absolutely essential in order to get anything done in a science lab, is to have that lab notebook. For engineering and an engineering lab notebook, particularly in this class, I'm not requiring paper notebooks, but I do expect people, if they've done some measurements with pterodact, put the metadata in there, explain what the experiment was in the notes, save it in a file. Save it in a file with a name that you can later find it with, not just file 1, file 2, file 3, but actual things that can help you find your data when you need to double check something. Correct your homework. When you get homework back in this class, almost all the homework, almost all the pre-labs are there to set things up so that you can get the design right for the lab. If you made a mistake in that preliminary thinking, you can't just say, oh, I lost a point, throw it away, because that hasn't cleared up the misunderstanding in your thinking. You're still not going to be able to do the design. So whenever you get homework back, quizzes back, pre-labs back, look for every point you missed and go, what did I do wrong here? What's my misunderstanding? And if it's just, oh, I did it again and I see I screwed up there. I put a minus sign when I should have a plus sign. Now I understand it. I've got it right now. Great. Other times it's, wait a minute. I did it again. I'm getting the same answers before. Why is it wrong? What's going on? Then you have a deeper misunderstanding and you should ask for help. You say, I tried redoing this homework and I'm still getting this answer. Where's my mistake? And then, sort of thing office hours are for. I can help you step through it. I can ask you to walk through doing the problem and see where the misunderstanding is and help you clear up the misunderstanding. And debugging your thinking is the same problem in a different medium as debugging electronics. I can't tell what else is going on in your head. So you have to give me, all right, this is what I'm expecting, but this is what happened. This is what I'm expecting. And then I can start going, oh, wait a minute. Why were you expecting that? Back up, find out, oh, you had these two concepts swapped, or, help find where the misunderstanding is by looking at the subparts and trying to figure out where along the way something went wrong. And I mean, you can do that with your own thinking to some extent. Sometimes it's easier to do in somebody else's thinking, but it has to be observable. You have to be able to sort of talk through the problem. And talking through the problems with your partner often will help you find these sorts of misunderstandings. So your partner go, wait a minute, that doesn't make sense. And then you can sort of work out, okay, does it not make sense because your partner doesn't understand it, or does it not make sense because you didn't understand it? So always correct every one of your homework problems, every one of your pre-lab problems. Make sure that you understand what went wrong and that you can correct it, because otherwise you're going to get stuck trying to do the design. And when you ask for help, which I encourage people to do, ask for help intelligently. Don't just say, I don't understand anything, because nobody can help you with that. If you don't understand anything, there's nothing that can be done. But if you can say, well, I did this, and I got this answer, but that was wrong, it's possible for somebody to go and go, wait a minute, you skipped a step here. How did you go from here to here? And start drilling into where is the misunderstanding. So, because debugging is what teachers trying to do when they're trying to help you, they're trying to debug your misunderstanding, they're going to need to know what's the expectation, what's the observation. And if you can't say what you're doing, it's very difficult for anybody else to get inside your head and figure it out. So try to be very clear about what you were expecting to see, what you did see, what the difference is, and why you're, if you can figure out where you're confused, it'll help somebody unconfuse you. In electronics, a lot of times there's a big question of, is the problem in this design, is it in the design? Or is it just in the implementation? Is the design perfectly good, but the implementation doesn't match the design? So, if you've got an expectation and observation don't match, is the expectation wrong? Would the design never have worked because you had the incorrect understanding of it? Or is it, well, that design should have worked just fine, but it didn't, so there's an implementation problem. What you built doesn't match what you designed. And trying to narrow down that problem is an essential part of debugging. And it helps to work through your expectations with your partner, to work through them when you're asking questions. You say, okay, this is what I was trying, here's my schematic, this is what I'm trying to build, this is what I expect to see here, here, and here, but this is what I actually see here. That can help a lot in somebody helping you do the debugging. Okay, that's probably enough on generic debugging. I'll do another video on stuff that's specific to electronics.